It is now my pleasure to turn today's program over to Dr. Peter Hurst, Associate Dean, MIT Sloan Executive Education. Sir, the floor is yours.
Thank you very much, Tony. Hello, everybody. Good morning, good afternoon, or good evening, wherever you are in the world. Welcome to the 20th in our Innovation Network webinar series from MIT Sloan Executive Education. On this 20th broadcast, I am here with Dr. John Carrier, a Senior Lecturer of System Dynamics at the MIT Sloan School of Management. The Innovation at Work webinar series, as I think many of our regular viewers know, is a way that we bring the work from our executive education faculty to a large audience to learn about and talk about the latest applications of their research. You can find out more about our other webinars and programs on our website, executive.mit.edu. Dr. John Carrier, Senior Lecturer at MIT Sloan School, is a very prolific researcher and practitioner and consultant in the application of systems thinking to business in general and manufacturing and operations specifically. And Dr. Carrier is going to talk a little bit more about some of those ideas with us now. But today he's going to talk specifically about the Internet of Things, the industrial internet, and what we all need to know to ensure that we're able to be successful in implementing the next industrial revolution. So I'm going to hand the control over to John. Later on, we'll have some quick Q&As, so feel free to ask questions in the chat forum, and we'll come back and try to address your questions towards the end of the webinar.
Great. Thank you, Peter. And welcome, everyone, and thank you for joining today's webinar. And just to set a little background, when we start to think about the industrial Internet of Things, it's really part of what's being called the fourth industrial revolution. And let me talk you through how that really worked. The first industrial revolution was really about technology. So, for example, if it's the Middle Ages and you wanted a shovel, you went to a blacksmith and he made you your shovel. So what you had was very large product variety, but very small volumes, and they were very expensive, and you had to wait for it. The second industrial revolution was really mass production, and the best example here is we're thinking Model T automobiles is mass production dramatically reduced the cost of making these items, and you could have them right away. The only problem was you basically got the same item as everyone else. The third industrial revolution was all about bringing information and computation into the picture so that now we can start gathering information on mass customization, and now also in terms of supply chain, we can move things around the world in terms of globalization. And it turns out the fourth industrial revolution is actually folding back onto itself. And where we're getting is we basically want all the benefits of the first industrial revolution, customized products, with the benefits of the second and third, that we want it now and we want it cheaply. So in other words, what we're trying to do with the industrial Internet of Things is to perform the following. We're all trying to increase the variety of products we make on shorter lead times, smaller runs with flawless quality, automate where we can, and mechanize, but keep our systems flexible while also minimizing capital and keeping our workforce contented, right? Now, what's interesting about these words is they were actually written by Professor Wickham Skinner of Harvard Business School back in 1966, right? So the question we're asking ourselves today is what's really changed in terms of the industrial Internet of Things? And my perspective is this. I've spent 20 plus years working in petrochemical and discrete part manufacturing systems. So I've been involved in creating large scale control systems in many of these plants. But what's really changed is the cost of doing it has dropped by several orders of magnitude. And that includes your sensors, your actuators, your ability to network and communicate, and then do computation on those and communicate the results. And if you've seen any of the recent reports on the size of this opportunity, it's all in the $1 trillion range under this fourth industrial revolution. Here's the interesting part. is recent studies done separately by Cisco and the Boston Consulting Group actually indicate that managers are reluctant to invest in this trillion-dollar opportunity. And our belief here is it's actually really a systems issue that's holding all this back. And let me give you an example of that. And let's step back to 1973. So just as a side note, I collect slide rules as a hobby. And I came across this slide rule from 1973 from the Faber-Castell company, right? And what the Faber-Castell company was trying to do was to introduce their new calculator to a group of engineers who were using the current technology of slide rules. But they were actually encountering difficulties with adoption. So what did they do? So you can see the front of the slide rule there. Take a guess what's on the back. And what you'll see there is on the back, yes, they placed the slide rule on the back of the calculator. And by version 4, the slide rule was gone. But the issue here is it's not simply the technology that we have to worry about. We have to worry about the system in which it's being adopted. And the companies and services that figure that out first will be the ones that build the biggest base and the ones that come out winners in the industrial Internet of Things era. So the way we are currently looking at the IoT is it can be looked at, it's a low-priced commodity. And any of you are free to go on a service like Amazon and see that you can buy a sensor, a communication device that's wired to your internet, and will allow you to produce a dashboard that can be seen anywhere in the world for under $100. So again, the manufacturers and operators are going to win are the ones who adopt the technology best into their own system and change their own dynamics. And the suppliers who will win will be the ones that make their products easier to adopt, not necessarily the one with the best features. And if you stop and look at the industrial Internet of Things in terms of platform, it can be divided into 4 major parts: connectivity, cloud, big data analytics, and application development. I'm not going to go through all the individual features in these boxes, but if you do, you can see that any of those features are basically available for anyone of any company scale on a rental basis. So there's going to be very little barriers of entry in terms of capital or in terms of technology. And where that takes us to is, if this is what the industrial Internet of Things offer us, is our system actually ready to implement it? And here's a photograph that I took of a recent facility I visited back in October of 2016. It is a 100-year-old family-run business. And if you first look at this photograph, it looks like it could have been taken in the 40s or 50s because there is not a lot of new technology. But I want to point out a few specific things about this photograph. First, you'll notice the tools are very well organized in a line. That means the shop knows what they're doing and they know what tools they need to do the work. Second is, if you look at those gray boxes, those boxes, also known as Kanbans, really control how the work flows. Now, they're not unique in having boxes or bins and controlling the flow of the work. What is unique was how few boxes they had to control the amount of work that they put through their factory floor. So not only we learned that their tools boxes are organized, the flow of work is actually well organized. The third thing I want to point out is, if you look in the middle right portion of the photograph, you will see a pencil sharpener attached to the workstation. And the reason I picked that out of the photograph is this was a shop where everyone recorded every 15 minutes with a pencil what they were doing, and at the end of the day, they analyzed their work. Now, of course, most shops I see that I visit are capable of doing that, but don't have the discipline to do that on a 15-minute basis. What the industrial Internet of Things offers us is the ability to take those measurements real time, distribute them everywhere, yet bypass the discipline of having our own employees stop to record that data themselves. So in fact, this shop, although it may look relatively primitive in terms of technology, is actually very ready to start implementing parts and pieces from the industrial Internet of Things, because what's going on in this shop was observable to me and it was stable. So the next step is, in terms of your system, we like to dig down deep and actually try to implement a specific incident of the industrial Internet of Things rather than trying to buy it as a massive package. And what we mean by that is, could you actually go into your shop and implement an industrial Internet of Things application in 1 day or less? And in order to do that, you will find yourself working your way through the IIoT stack. And what that means is, at the bottom level, which is number 1, I need a sensor. And then when I have that sensor, which could be measuring temperature, humidity, it could be measuring tooling speed, any of those measurements, it has no value in itself unless I can connect it to something, step 2, and then bring it somewhere where I can do some analysis and computing, store it, and then finally abstract the results. So we've already stepped through 5 levels of the stack. Then we need to bring it into an application so we can use it on a routine basis. And then finally, we need to share it with our teams so we can collaborate and improve our shop. Okay? And until you go out and buy a full IoT implementation, I would highly advise that you actually try to take one area of your shop and try to specifically implement one instance of IIoT. And what I'd like to do is, I'd like to show you how we did it. So back in November 2016, one of the factories I routinely visit was going to buy a very expensive, for them, Akuma numerical controlled machine to basically make parts. And a shop like this cannot afford to implement new equipment and not have it work almost from day 1. So this shop did an interesting thing. You can see the photograph. They are using their own employees to prototype what the cell is going to look like, which is fantastic. Then, about 4 weeks ago, the expensive machinery arrived, but they had no way to measure how that machine was performing in their cell. And they were going to have someone sit there and just constantly measure cycle times of all these new products that they were testing. And what's important about that is, it's very difficult to capture that information by pencil. You're using different sets of operators, and then the amount of work to actually translate it into electronic signals is very difficult. So we found a company that was implementing a point solution for the industrial Internet of Things, and it does a very interesting thing. It simply plugs into your between your device and the power supply, and it measures the amperage as a function of time, for which I'm showing you the raw signal. And it can take that raw signal and turn that into machine cycle times and broadcast to any mobile device in the world. So literally in less than a day, we took a brand new cell with relatively primitive recording techniques and took it into the industrial Internet of Things. And why that's so important, and this is the quote I got from the plant manager, he said, normally, when I want to see what's going on out in the factory, I have to walk out and see it. That means at best, I can track what's going on every 2 hours, sometimes only half a day. Now, we can see how the machines are running real time, so we can get out, and if some sort of action or remediation needs to be taken, they can do it immediately. And it's that lack of visibility that we were able to solve with a relatively low-cost solution in less than a day that's really going to help your internal system when you're moving to the industrial Internet of Things. Now, the second part, aside from straightening up your own system, is actually moving your factory or facility onto a platform. So we've talked about your internal system and how these lower costs of services and access to sophisticated algorithms and power can help you straighten out your own shop. Your second step is, what does this mean once our own system is cleaned up about putting ourselves on the industrial Internet of Things supply chain in terms of our own industry? And what it's going to do is provide end-to-end real-time transparency through a common language. And it's going to add additional benefits through visibility that qualifications of suppliers and new product development and leading indicators of failure are not simply available to people on the shop floor at the moment, but are basically available to anyone in your entire supply chain. And just as a quick example, this is a platform diagram for automobiles showing the connected car landscape. And what I really want to show here is this shows the overall platform and the specific point solutions within it. My job is not here to talk about all the services that are offered for this landscape, nor who the winners are going to be. But the one point I would like to make is not all the companies and factories and facilities that come into this new world are going to survive. And those who come on and basically destabilize this platform because their own systems aren't stable will not survive. And that's where we get into the 7 system properties that you're going to need to know when it comes to taking your own system into the industrial Internet of Things and the 4th industrial revolution. And the 7 are these: observability, controllability, stability and chaos, metrics and optimization, feedback, variation, and finally, understanding that the data is not the system. And I'm going to run through each of these individually and give a simple example. So let's start out with observability. So observability simply means, can we see or measure where we're going? Or if you're driving a car, are your eyes open? And I want to take this to a real example I saw, and this comes from the retail industry. I was going to buy my lunch, standing in line, and when I got to the front of the line, I saw this sign. If we don't give a receipt with your order, then your order is free. Now, this really confused me because as a customer, if I wanted a receipt, I would ask for it, wouldn't I? So why did someone go to this trouble to put up this sign? Well, I thought about it from a systems standpoint, and I realized I'm not the beneficiary or customer of this sign. The manager is. Because what is the manager trying to do? It's unfortunate, but in this industry, when an order is done in cash, the person at the cash register may simply take the cash and not register the order. And the manager couldn't see this. So the manager putting up this sign turned me, the customer, into his sensor and into his feedback signal. It was an exceptionally clever implementation before the industrial Internet of Things. But in most places I go to today, it's this type of missing observability that I think is going to be phase 1 of the IIoT. And as an example, I visit maybe 15 to 20 new facilities every year. And the common question I hear from most facilities is, I want to know what my machine's doing today, right now, and I want to know what it's going to be doing in the next 30 minutes. And as you saw from that previous example, we were able to supply a facility with that type of capabilities within less than a day. And that observability changes the way we run our operations and systems, and it also makes it easier for our customers and our suppliers to serve us and for us to serve them. So the second system property is controllability. And I am a chemical engineer, so I like to think of it as how many valves are on our pipe. And it looks something like this. I know we've all worked on projects where we had a great opportunity and we come up with a business case for why to do it. So we basically turn on the valve to make that happen. Nothing happens, okay? And then we start to realize what's actually starting to hold back our productivity is there are hidden valves in our system. And if you've ever been involved in any system where decisions are made, you'll find there's not only the financial and operational justifications, there's also the political and cultural valves that need to be found in your system. So second is, when you design the IoT systems, you're going to have unlimited access to low-cost sensors and valves. The danger is you're going to put too many valves on systems and you're going to actually lose control. It's almost like putting 2 steering wheels in the same car. So actually mapping out the information flow and agreements as well as mapping out the facility is going to be exceptionally important to delivering the value. The third principle is around stability and chaos. And the way I think of this is, all our systems are very much in common. They all act like springs, no matter what industry you're in. And it turns out to actually remove the dynamics of that spring, we have to subtract things from our system. And it turns out that subtraction is much harder than addition. So I would like to take you back to 1958, and it was our own, here at MIT Sloan, Professor Jay Forrester, who invented magnetic core memory in approximately 1955. He was asked by General Electric back in 1958 to solve a very difficult problem they had. They had a refrigerator manufacturing facility in Kentucky, and they found on a month-by-month basis, some months they'd be running 3 shifts, and couldn't make enough, and other months they had barely enough work to run half a shift. Now they know that's not the pattern that customers buy refrigerators, so they were wondering what was causing this issue. And what Professor Forrester did was he set up a simulation that we now call the beer game, and it's played at every business school in the first 2 weeks of their arrival, and it simulates a supply chain. And what it does is, if you think of any supply chain, on one end I got a customer, and on the other end I got a supplier, and in the middle we put various intermediaries, including a retailer and a manufacturer. And what happens is, when you simulate this, even if you simulate it with bingo chips on a picnic table, as we do here at MIT, you will see that a small amount of variation in a customer order starts to get amplified as we move up the supply chain. And you can see in this example from Professor Forrester's paper, is you start getting massive spikes that are 10 to 20 times the actual size of the variation in customer orders. This is a very difficult way to run a supply chain, and our question is, why does that happen? Well, it's because of all the time delays we've put into this system. And what's incredibly beneficial for the industrial Internet of Things is we have the opportunity to either dramatically shorten those time delays, or if we're not careful, we can actually add to them. And what I'd like to do is, I'm now engaged in another industrial Internet of Things application at a furniture facility in the Midwest, and I asked them to play this beer game again. So you can see the photograph. They've laid out their full supply chain simulation in about 15 minutes. And when they played that game, they actually saw the same phenomenon, that when I start out with a small change at the retailer, it starts to get magnified by a factor of 2 to 4 by the time you move back through the supply chain. And if this is an opportunity we can address with the industrial Internet of Things, that will start to revolutionize supply chains. So as we continue along this theme of system dynamics in a supply chain, we need to understand a system's complexity. And I like to look at complexity in a system in terms of 2 ways. One is the system itself, what it is, and second, what that system does in terms of performance. So very quickly, no one will disagree, a watch is very complicated. It has lots of moving parts. But when it's performing correctly, its performance is very simple. There's only one way that it works, right? So 1 cycle is 1 second. Now, I'd like to show you another complicated system, and this is from my own experience on a project working on a natural gas rig move in the middle United States. That's also a very complicated system with a lot of moving parts. But you can see on the right in the red diagram that the behavior of moving this site back and forth was exceptionally complicated. And to cut right to the direct answer, I went out and counted how many items that they had on site to know how many we had to move to perform an optimization. And here's what I found out. They did not even know how many trucks they had on site. They thought they had 10. They actually had 30. So our first step was to actually count everything on site. And we actually removed half of the tools because they were never used. And that simple action basically cut their variability by half, as well as made a more stable system downstream for their suppliers. Now, this was done in the quasi era of industrial Internet of Things. Now think that we can automatically track all these instruments and devices real time, and we will be able to guarantee that performance across any system. Fourth, I want to talk about metrics. And I like this one to call this how to win at a fire drill. So one of my first jobs at a new company was I was responsible for running the fire drill. And how that works is the alarm goes off. The first person comes out at maybe 30 seconds. Then you have a median at about a minute. The mean person, or average, comes out about a minute and a half, and the last person comes out in 2.5 minutes. And the way the building was designed was the fire basically takes over the system at about 4 minutes. So the fire sets the goal. And I go into so many systems, and we're always trying to optimize or get better or be first in class, when in fact, and everyone knows this in most operations or manufacturing, you're not always measured by your best. You're measured by your worst. And simply by understanding and selecting the right metric is going to determine the difference of being successful and failing. And I like to add this example, and this is a quote from Randy Pausch from Carnegie Mellon, who said, "Doing things at the last minute is much more expensive than just before the last minute." And it's a great quote, and in order to do that, it means you must understand the time behavior of your system very well. And the IIoT provides a fantastic opportunity to collect, store, and analyze timestamp data. The fifth principle is feedback. Are we learning or just repeating? And here's an example. I visited a weld shop, and this weld shop was serving a very expensive and valuable petrochemical plant. And the challenge in this scenario is if your part doesn't get done on time, you're going to miss the turnaround window. So if the part's 1 week late, it's not going to get implemented in the facility for potentially another 18 months. So when I went to work with this shop, I talked to the welders and said, tell me about your job, tell me about when the torch is running, what keeps you from doing your value-added work? And they said, well, you're a little bit late because before we used to spend a lot of time scrambling to get the right parts, the plans weren't right, we were welding to similar metals, and we installed someone to actually check to see that defective plans weren't reaching us. So basically we went from a 70% uptime, i.e. when our torches were on, to a 90% uptime. So we're actually very good, no need for improving our own system. So I sat back and thought about it. I realized, you know what the problem is here? So when the inspector gets a bad plan, he or she simply sends it back to be redesigned and sent back. So they have literally institutionalized this 20% defect rate from the designer. And the other point that they missed was, although the welders are busy and everything they're getting is on time, if I were one of those people who received a defective plan that were sent back, I had to wait 6 weeks and the welders never knew about it. So this is actually still has a broken system. And the reason why is they put in corrective feedback, i.e. I catch the defect and send it back upstream. But what they didn't do was put in adaptive feedback. I shouldn't simply send back the plans to be corrected. I should be collecting statistics on what went wrong and sending back a Pareto chart to the upstream designers and said, please don't send me these defects again. And that's an important difference, that we don't always differentiate between corrective and adaptive feedback. And it's that adaptive feedback that actually allows us to increase our operational IQ. Number 6, around variation, the product is not the process. And this is how I explain it to my classes is, think about you're going to the store and you buy a tomato. And it's a very good tomato. You pick it out, you really enjoy it, and you enjoy it so much that you decide you're going to start your own pizza shop. And you want those tomatoes. Well, now you're not just buying one tomato every few days. You're going to be buying 10,000 tomatoes per month. So what that means is, in the first example, I'm simply buying your product, right? In the second example, when I'm buying 10,000, I am now buying your process, right? And what that means is we're going to have a very close relationship with our supplier. In the past, that's meant months and months of on-site inspections and working with our new suppliers and qualifications. With the Industrial Internet of Things, we're actually going to have real-time access to their control charts and their machine uptime. So the ability to qualify and bring new suppliers into your supply chain is going to change dramatically. And the companies who can figure out how to make themselves easy to be incorporated into their downstream customers are going to have a tremendous advantage. One quick example from my own experience. This was a furniture factory also in the Midwestern United States. They were struggling in 2009 like everyone else, and their number one competition was China. And when I asked them, what's the real challenge? Well, they can compete with us on price. Then I asked them, how long does it take for your customers to get a product like yours from China? And they said 9 weeks. So I said, I took a look at your process from your financials. You know how long it takes your customers to get a piece of furniture from you? 9 weeks exactly. Actually, sometimes up to 12. And this is surprising because they only put about 4 pieces of labor per each piece of furniture. And how do you actually build this system dynamic disadvantage into your system? Well, what they did, they basically built up 90 days worth of inventory so that they could make up for the 10,000 miles of disadvantage their competitors had in China. So again, you're buying a piece of furniture, that's one thing. But if you are a retailer and you are bringing in furniture from suppliers, if I actually sell the piece of furniture I got from you in 1 day, I now have to wait 90 days to get my next order. So it's actually the amount of inventory in your system that controls your dynamics, which is a little bit shocking because it's the boring thing. And so what we focus on here is very much watching your level of inventory because that controls your dynamics. And then finally, the data is not the system. And I'm going to go back to an example from, this goes from the automotive industry, from a gentleman, Henry Ford. And Henry Ford pioneered the moving assembly line in Highland Park, Michigan, and figured out how to build one product very, very cheaply, very effectively. And at that time, an external accounting group went to analyze the different car companies' systems for their financial tracking. And most of the car companies, their competitors, had roomfuls of accountants. And so their auditing committee was, this is really good. And they went into the Ford facility. They didn't have a large group of accountants measuring costs and tracking invoices and accounts receivable. They simply had a scale. And the plant manager put the stack of account receivables on the scale. He measured it, and that's how he estimated their accounts receivable. That was seen as being very primitive. But if you look at it from an information standpoint, and this is where we introduce another MIT professor, Claude Shannon, it's not the volume of data itself, it's the value of the information that it provided. And if you realize this system was actually genius because I probably got a better estimation of what the accounts receivable was from weighing it on a scale than I did with a room full of accountants. And second, I could get that measurement in real time. So as you start to implement the Industrial Internet of Things, before you start wiring up every piece of equipment you can and collecting every piece of data, think about what you're actually going to do with that data, okay? And finally, when I go into most systems and companies, I found that when I show them this very simple graph, it tends to generate the most discussion. And what it really means is the data is not the system, and the system is not the model. So very quickly, have you ever heard the term data warehouse? That is not a good name, because that means the data is not flowing and we're not using it to fix our system. Second, do we ever find ourselves in meetings hypothesizing how our system should work? That means we're not collecting data and checking against what we think it should be doing versus how it is actually performing. And then finally, if you are a data scientist or analyst, I very much encourage you that when you collect that data, the first thing you should do is take it into the system and talk to the people in it so that you can understand it and interpret it. Because at the end, the real value of the industrial Internet of Things is better understanding that system we're in. And those are the 7 system concepts. But what's interesting, they actually align against a single concept, which is called the hidden factory, and how we plan to solve that, which is using something called Little's Law. So let me introduce you to those concepts. So first, let's look at your system. So when I visit any factory or facility, the first thing I get is, here's our process on a piece of paper. Well, that's not really your process. Sometimes it is, but if you actually go and observe what's going on, you'll often see a defect happen. And that defect often flows downstream until it's caught. Now, of course, those in operations know the first thing we do is we panic, right? Then we grab that defective item, we fix it as quickly as we can, and then we figure out where to put it back on the line, right? And I would like you to know, not only do I work in factories and facilities, I also work in slides and presentations, and I can tell you it happens there too. Now, that's a good thing in the short term because we fixed the problem and we didn't keep the customer waiting. Here's the problem. When we come back tomorrow, we do it again, again, and again. And pretty soon, 30 or 40% of all the work we do in our system is done through one of these hidden factors. And Dr. Feigenbaum, who graduated from the Sloan School in the mid-50s, found this on the 3rd day as operations manager at a manufacturing facility here in Western Massachusetts. That's what he saw in 1960. That's what we currently see today. And there's one challenge, and it's this. When he chose to name it the hidden factory, he picked an excellent name. It's very hard to see. So what we do here at the Sloan Schools, we also have our own Professor John Little, who in 1961 proved the following relationship, that the inventory is equal to, or work in process is equal to the production weight times the amount of time that item or product spent waiting. So what I do in most facilities is they can always tell you the production rate, or lambda, how many did we make today? That's not the question I'm looking for. I'm looking to know how long did it take to make your products from start to finish on a distribution. And if I know that, it starts to give us information that there are things waiting in your process, and they must be sitting in a pile. And that pile is where the hidden factory is. Now I want to show you a blow up of that graph. If you make this in your facility or in your operations or even in your knowledge work production and you measure cycle times for your product, it will look something like this. And you can break it down into 4 parts. The first one is something that took much, much longer than any other products. That's usually a special cause failure that people know why. The second one is where things take 50 to 100%, maybe twice as long as they should, and that meant something little went wrong, and it got fixed in a hidden factory, yet no one usually records what they're doing. Step 3, that's what our process normally runs, and that's what we're currently capable of. And step 4 is if you've ever worked in a system where the CEO wants something for one of his friends, that gets done immediately. But the point here in terms of industrial Internet of Things is I very much encourage you, spend your time to find those hidden factories and remove 2 first before you start improving 3. Huge benefits. And again, it's those items in step 2 that are done last minute that are going to end up that be very costly and will ultimately lead to a degradation of your system. Now, as you go forward, we've put together a framework for building your system IQ as a way to incorporate the industrial Internet of Things in your current system. And the point here is you'll see on the right, we're taking the tools from 100 years of continuous improvement and industrial learnings and matching it up against some of the opportunities and things we need to do to make a system better. Start with preparation, observe how it behaves, make corrective feedback, and then adapt to get better. And it's very clear that these tools are very effective, but the industrial Internet of Things makes implementing them much, much easier. And also, if you do have a Six Sigma, lean, or continuous improvement effort at your facility, the industrial Internet of Things can greatly accelerate their progress and take it to new heights. So finally, just where we're going is we want a facility that can do 2 things. 1, make what our customers need to do today across the top line. And then at the bottom, as we're learning, if we do make mistakes, we pull them off the line quickly, we correct them, then we learn and adapt. And that is an intelligent system. Okay, we talked a lot about systems and operations and making improvements in a lot of the technical pieces. I just want to make one quick note about culture. This is a note from the wall I found walking around the Sloan School on the wall. It talks about culture as a problem-solving device. And what happens is people faced with the same problems invent their own culture to solve them. And there's really 2 points here. One is, if there's problems, before you try to fix them, start to understand the culture that's built around solving that problem today. And second, try to leverage and build that culture so that you become a problem-solving organization. And you incorporate the new ability to bring in data and automation in with the people in the problem solving. And that quote, of course, comes from our own Professor John Van Manen, an expert in culture, corporate culture, and has been here at the Sloan School since 1972. And I do have the privilege of teaching with him, which is fantastic. And then just to wrap up, know thy system. And we don't understand our systems as well as we think we do. The industrial Internet of Things can help reveal it to us, provided we know what we're buying. And then finally, look for when your system starts to desynchronize. That is a sign that your system's starting to basically degrade, and it's a perfect opportunity for the industrial Internet of Things to unveil that desynchronization and help get you back on track. And then our last quote from Kurt Lewin, who was here at MIT from 1945 to 1947, and an expert in culture as well. If you want to understand a system, try and change it. Okay, so thank you.
Great, thanks very much, John. And I'll move back in now to take over with some questions and answers. We've had some people asking questions as we've been going. I'll try to summarize those. Feel free to keep asking questions through the chat function if you have any. But just to get us started, John, one of the things that was very fascinating to me and many of the people listening to this presentation was we tend to think of the Internet of Things as conjuring up a very high-tech sort of, whether it's in manufacturing or other areas, way of looking at the world. And yet some of the interesting examples you've talked about have been in quite traditional manufacturing settings, in furniture manufacture, for example. Perhaps you could just say a little bit more then about, from your experience, how it is that these ideas apply equally to a mom-and-pop manufacturing facility somewhere in the Midwest to a giant multinational that's fabricating semiconductors around the world.
Absolutely. So first, I'm going to start with a example from my own kitchen, of which I'm quite ashamed of, by the way. Many of you may have heard of a Kanban system, or if you haven't, it's basically it's a Japanese word for order or card, and it's sometimes implemented as boxes as you move parts back and forth. Well, I was watching the other people in my kitchen work, and I realized the trash was building up. And when the trash builds up, it changes the way everyone else works in the kitchen. They stop throwing things away, they stop stacking their work, and all of a sudden you start to build up this tremendous mess. Well, I realized my trash can has a Kanban in it. It's called the top. When it gets full, that trash must be taken out. If it's not taken out, it keeps the most valuable people here, the cooks, waiting and doing tasks that don't really add value. Now that's in my kitchen, but I've actually seen the same with surgical teams, right? And obviously, if you look at a surgical team, you want them to be doing their surgeries and not being interrupted to grab tools or other items to get their work done. And what's interesting is hospitals have a name for this. They call it top of the license, right? So when I go into any system, I look at what's most expensive, right? What's a minute worth in this entire system? And the example you gave, Peter, is semiconductor systems are very expensive too. And I ask, what are the small things that are going to keep it waiting, and what do we do about it? So really, the technology from the IoT has helped us to find it rather than the technology itself.
So this is a really fascinating kind of juxtaposition of these two very different realms. For me, it brings to mind, and we have some questions about this as well. You've talked about what sort of the capabilities that I think the sort of leaders and managers in organizations that are trying to implement the industrial Internet of Things need to have. And one of the things that we keep coming across is this culture, the connection between IT, information technology, and OT, operating technology. And these are two very different historically kind of disciplines and cultures and kinds of people. So as you've been doing this work, how have you encountered this kind of internal subcultures within companies, and what kind of approaches have you found that work to be able to sort of to get past those barriers?
Well, it's interesting, Peter, because I'm from the operations side, and I've had 20 years of operational experience, and typically we sort of control things, and then when something went wrong, we went and chased down the IT people to serve us. And I was just having a course last week, and guess what? The IT people now run the roost, and we now respond to them. And I think the biggest issue that's going on is now IT must be included in any operational plan. Plus, when we're now talking IT, what they're working on has the capability of shutting down the entire plant, okay? So that must be very well understood, and they must be part of the operational plan. And then second is, and this has only been in the last year or two, is the language between the IT and the OT has to be developed, but the most important one is that the IT do understand from operations. It can be very dangerous to shut a piece of system down to put a patch in. All of those things need to be prepared and simulated before you actually go online. So I think it's going to be a huge opportunity for collaboration between those two groups. The companies that develop cultures where the OT and IT work together will be successful, and they will gain ground over the companies that they silo traditional roles.
So that's in terms of these two groups are important for building and operating. The other aspect that you talked about was the capability for throwing off huge amounts of data from these processes. And so this is a new kind of role and job function that we're seeing becoming important as well in terms of the data science and analytics. So do you have any examples from your experience of where those analytics have actually really come back into the skill sets and capabilities of the engineers or the IT people and how those interactions occur?
So I do. And it goes back to, this is, again, from another chemical facility. And the reason I use that example is they've been collecting giga and terabytes of data for 10 to 20 years, and they store them in these things called data warehouses, which means the mental model is the data sits. So refineries are a very complicated piece of equipment, lots of feedback. And when I said, let's look at the timestamp data, and let's just look at the variation in time for a specific type of task in an area that's $1,000 a minute or more. So literally, we went from this dusting off this huge gigabytes of data, turning it into a relatively simple Pareto chart of cycle times. That's that W graph I showed you earlier. And we go, this is varying by 10 or 15 minutes when each minute's $1,000. Why did the one we did today cost $20,000 more than the one we did yesterday? Now, here's the part where I think big data matches to the system. We immediately wanted to blame the operators, right? But I know better because I've made that mistake. I took that chart on a piece of paper into the field and showed it to the operators. They started laughing, and then they said, come here. And what they did was they showed me a specific piece of equipment that they've been trying to get replaced for years. So my advice is a lot of the tools and techniques are out there, and it's better to, when you take your data, do a relatively simple analysis and take it back into the system rather than build a huge data analysis capability without checking.
Great. So as you've looked at these and helped with these sort of implementation projects, back to this theme of IT versus other kinds of engineering, one of the things that we hear about is there's a lot of talk about agile and agile development now. Is that the right approach for implementing IoT, or traditional engineering disciplinary approaches relevant as well, and how do we connect those things together to make them successful?
Okay, so I feel the term "it depends" is coming out. So first I want to say is, and I'm going to define this at a very high level, what Agile lets you do is develop things very quickly you can test, but they have a lot of defects in it. And if I'm in a system that has a lot of unknowns on unknowns, like I don't have clear specifications, I should do something agile so I can see how it works, and then all those defects will tell me what the specs are, right? Now, if I'm going to implement something in a chemical facility where shutting it down is a couple $1 million a day, plus it's dangerous, I have to use I have to very much have that all the defects worked out in very clear specifications. So what we're doing is run your agile experiments, then take the time to actually stop and design something bulletproof. And if you notice from the example I showed, the company who built everything on a cardboard when they built their cells, what they did was when they actually implemented the full-scale expensive piece of equipment, everyone was trained, ready to go, and a whole bunch of mistakes we could have made later were found in the formula. So it's all about learning what your mistakes are and eliminating them before you go on. But I greatly encourage anyone, try and experiments, right? And in your own facility, or go find someone nearby who's doing it. I really advise it.
Great. You talked there about sort of the sort of safety critical issues that might be important as well. How concerned are you about the sort of security and reliability implications of industrial Internet of Things? In particular, it seems like a lot of what we're talking about almost relies on the assumption that everybody's a good or at least a well-intentioned actor and we're trying to remove accidental defects. But what about issues of security and malfeasance and other kind of concerns I know a lot of people have about these systems?
So I've just started working with a very large cloud edge computing company that's a leader in security, and I learned things I did not want to know. So I'm exceptionally concerned about this issue, and what I'm asking people to do is one, just try your application and just put a few measurements online, not the whole thing all at once. And second, make sure you're keeping up on the advances in all of these, distributed denial of services attacks, et cetera, and so on. And look at the industries who need to be rock solid, like the nuclear and financial industries, to know best practices. And finally, if you do work for partners, maybe look at some of the big pockets who really suffer with your pain. Could be good.
Mm-hmm. So big business versus startups?
This industry is still evolving, and I think at the end, there's probably only room for a handful of platforms because of this common language effect, also known as a network effect. So I can't tell you who's the right place or who will be successful, but there will only be a few major platforms that we know. And then second is there will only be, when you do look at a point solution, try not to let that be incorporated so deeply into your processes so that when you need to select a platform, it's a problem. So look for interconnectivity as you go to the grid.
Very helpful. If I may put you on the spot as we're just sort of coming around to wrap up now, you've very convincingly offered to us seven principles systems thinking that we should keep in mind. If there's one thing that you think that you would advise people who are watching this webinar to do when they finish this webinar, or maybe when they get into the office tomorrow morning, that can help them on this journey in the most impactful way, what would your advice be?
Okay, so this advice hasn't changed in 20 years, but I'm going to update it for the IoT, and it's this. Right now, there's something going on in your system in a hidden factory that you don't know about, and you wish you did. And what I advise everyone, go see the work, right? And what the Industrial Internet of Things does, it makes it very easy to see what that work is because I can put sensors in specific places. And only second is, go see other people's facilities outside of your industry to how they're doing the IoT. They will let you in, they will show you things, and they will show you mistakes you will not bring back to your own implementation.
Great. So collaboration is the key.
Yeah, collaboration and share each other's mistakes and learn.
Very well. Thank you very much, John. You've also kindly put together some additional information that might be useful to people who are watching the webinar. First of all, John Carrier does teach in one of our several of our executive education programs, but one in particular on this topic, implementing Industry 4.0, leading change in manufacturing and operations, coming up in July and again in November. More information about that available on our website. And also, I think we have another slide with some further reading. Some of these are resources, I think, John, that you were drawing from, and people will be able to get more detail on those.
Yeah, and the recent Sloan article, 2 pages are partially on some of my work, so it'll be a great source to get started.
Okay, that's great. Now, the final thing I wanted to say is, John, you very kindly agreed to stick around with us and participate in a Facebook chat for those people who are able to stay here with us. And so we're going to ask Tony now to push the Facebook link to all of you participants to come and join us on Facebook for the follow-up chat. With that, formally, I'd like to thank you, John, and all of you around the world who joined us for this webinar. And hopefully we will see many of you on Facebook very shortly, and maybe some of you here at MIT in the future. Thanks very much, John. Thank you all for joining us.
And thank you, Peter, and thank you, everyone, for joining.
Thank you to all of our participants for joining us today. We hope you found this webcast presentation informative. This concludes our webcast, and you may now disconnect.